Hello. In this talk, I'm going to present the results in our recent paper, sampling from the plots on random graph of unbounded degree via the random process dynamics. And this is part of Random 2022. I'm Antonio Blanca, and this joint work with my collaborator, Risa Keisari. Okay. So in this talk, we're going to be considering the sampling problem for the POTS model, which is a classical probabilistic model that has application in an array of areas that spans statistical physics, computer science, discrete mathematics, and so on. So the model is defined on a finite, well, not necessarily a finite graph, but for now, let's assume that we have some finite graph G, and there is a set of spins or colors, 1 through Q. The configuration of the model are the assignments of spins or colors to the vertices. So every vertex will receive a color from 1 through Q, and the coloring of all the vertices is a configuration. In this model, every configuration receives a probability that is proportional to a weight, and the weight is given by this expression here, that is e to the beta times the number of monochromatic edges on the configuration. So for a configuration sigma, we count the number of edges whose endpoints have the same spin, the same color, and we scale that by a model parameter beta, and that gives us essentially the weight of the configuration. Now there is a normalizing constant C that is usually called the partition point. Okay. So here is an example. In this case, the graph, we have an example here where the graph is the 4x4 grid. And then we can see one configuration here. There are 2 spins here, so Q is 2. And there are 5 red edges, 7 blue edges. It means blue edge means that both endpoints are blue. So in total, we have E, the weight of these configurations is E to the 12 times beta. Right? And in this case here, the difference is that we flip these corners from blue to red, and that increases the number of monochromatic edges by 2. So we get that the weight of this configuration is E to the 14 beta. So the probability is weight over the partition function. Okay? So some important distinctions or special cases in this model is one of them is when we only have 2 colors, the Q equals 2 case, and this is known as the easy model, which is one of the most famous probabilistic models in physics and also in machine learning and other areas. Now, the model behaves quite differently depending on whether beta is positive or negative. And so when beta is positive, the model is said to be ferromagnetic because it is attractive in the sense that if there is an edge, the endpoints of the edge will prefer to be aligned to the same spin, and otherwise it's called antiferromagnetic because the opposite will happen. They will prefer to have different spins. In this talk, we'll be focusing exclusively on the ferromagnetic case, the positive case, beta positive case. Okay, so we want to generate samples from the ferromagnetic post model from its Gibbs distribution specifically. This is an important problem that has received lots of attention. For the special case when Q equals 2 for the easy model, we have a polynomial running time algorithm that works on any graph and for any beta. And this goes back to the seminal work of German Sinclair in '93, which was followed up by the sampling algorithm of Randall and Wilson in '99. Okay. Now, when Q is greater or equal than 3, when we consider 3 or more spins, then the computational complexity of this problem changes dramatically in the sense that we know now that this B is hard, which is kind of an intermediate complexity class, probably harder than P, but well, this is just showing that there is evidence that the sampling problem is substantially harder for Q greater than 3, and this is even the case for very special cases of graph. If we consider bipartite graph of bounded degree, the problem, the sampling problem is still bizarre. Okay. Now, this still, there are many cases, many graphs, and that show in applications and so on that we would like to generate samples from them, and maybe we can exploit some special properties of the graph, some special structure and so on, to make sampling possible and design algorithms. And this has been the case. There have been some success to some extent. So when we have really strong structure, very structured graph like trees and the complete graph, we get a very good understanding of the sampling problem there. In fact, we have very efficient algorithms. We understand Markov-chain Monte Carlo methods to sample from the Potts distribution, even with boundary conditions and so on. Now, but even for in other graphs that are also highly structured, but not so much maybe as the complete graph for trees, we see that the picture is not complete, the sampling picture is not complete, but there have been some progress. For example, if we consider CD or subsets of the high-dimensional inter-lattice graph, which it's quite relevant in physics, we now have a sampling algorithm that works for every beta, provided with a Q large enough. If we consider expanded graph, we have sampling algorithms that work for beta sufficiently large, which means this is the strong correlation regime when there is a strong interaction in the system, and this works for every Q greater than 2. And also when we take beta as small, which is the so-called high temperature regime, when the correlations are weak, we also have a sampler, and this one applies to any graph of bounded degree. Okay, so here is an interesting conjecture that I would like to pose, and this is kind of inspiring this kind of work, is that in all graphs of bounded maximum degrees, so that the maximum degree is bounded by some constant delta max, and for any Q, there is a conjecture that there is a near linear running time algorithm, provided that beta is below some threshold. And this threshold is the so-called uniqueness threshold for the tree, that essentially corresponds, in the tree, corresponds to a phase transition between the cases where there is only one versus multiple infinite measures that locally agree with the Potts measure. But in the finite case, this measure will essentially intuitively corresponds to vertices that are far, that some decay of correlation between the spins of vertices that are far apart in the graph, right? And the conjecture is saying whenever you have this type of strong decay properties, then the sampling should be possible quite efficiently, right? And there have been some progress in establishing this conjecture. For example, for Q equals 2, this is known. This is the theoretical work of Mossel's slide, where they show that the Glower dynamics for the easy mode, which is also called as the Gibbs sampler, which is a very simple microchain that in every step picks a vertex and updates the state of that vertex from the right local distribution. And they show that in this work, Mossel slide, they show that the mixing time is n log n, and this is the best possible. Okay? Now, the conjecture has also been established to some extent by this work that I just mentioned in the previous slide of Bodorevich, Greenhill, and Patel, where they show that this actually holds, but only for some constant beta that is below this uniqueness threshold. So there is a gap here that is open and has been open for quite some time, and yeah, so we would like to close this gap. And recently, with in an earlier work also with Risa, we show that this conjecture holds for random regular graph. Right? So if we draw a regular graph uniformly random from the set of all regular graph, then there is a sampling algorithm for that for the random graph, or for the Potts model on the random graph. Okay? But of course, there is still lots to be done. Now, in this work, we ask a slightly different question, and it's an important one that we should consider, is where this threshold is the right one, right? Where this beta u, this uniqueness threshold is the right one. And it is in many settings, but there is one particular case that is that was postulated before this work. That suppose that you have a graph where the maximum degrees is quite large, but the average degrees it's much smaller than the maximum degree, right? So the condition that beta is below the uniqueness threshold for the regular tree with degree corresponding to the maximum degree of the graph, right? may sounds like a very strong condition or unnecessarily strong condition for the sampling, because most of the graph, it's in most of the graph, the behavior, it behaves like essentially like a regular, like let's say like a regular graph with a much smaller degree. Okay? So I guess the question here is, which one is the right threshold to obtain an efficient sampling algorithm, right? If you want to think of an example of a graph, think of a random regular graph where we plant a vertex that has very high degree. Okay. Now there is some caveat here, and it's that it's not very easy. It's not very hard to show that if we consider the global dynamics for the descent and the Potts model, even if there is a single vertex of high degree, that vertex slows down the convergence of the global dynamics, and the mixing times bound that are possible are going to depend exponentially on the maximum degree. And this is the type which should be exponential on the maximum degree of the, which could be quite bad, right? For in that example that I told you, where we plant, let's say, a vertex of degree root n, you will get a bound. With the easy input explorer, we have an e to a root n bound. Requires that many steps to converge. Okay, and in this work, what we show is that for a general class of random graph, and in these general random graph models, there are many cases where the random graph will have maximum degree much larger than the average degree. We have efficient sampling algorithms, near linear running time sampling algorithms, when beta is below the uniqueness threshold for the average degree, not for the maximum degree. Okay, so that's our main result. Let's formalize first the random graph, random graph class that we consider. So in this kind of a standard model of random graph, we have a degree sequence where every vertex we require each vertex to have degree given by a sequence. The vertex I have degree di, and so on. And then we would like to sample a graph uniformly at random from the set of all graphs that has exactly this degree sequence. Okay, and our results will hold with high probability for graphs that are sampled from this random graph model, provided that the degree sequence is graphical, and this is a necessary condition. It means that there are actually graphs that have this that this degree sequence is realizable by at least one graph. And there is this other technical condition here that essentially says that the average degree of the graph is bounded. So this is what we call that the effective offspring distribution that corresponds to the distribution of looking at the degree of a vertex sample from the proportional to the total degree of the vertices that have that degree over the total degree of the graph. So the idea is, so the intuition here is that if you have a vertex and we're trying to pick a random neighbor, what would be the degree of that random neighbor that we choose for the random graph? Okay? So we require that this distribution has bounded first moment, and then that it also has a finite higher order moment for some, at least for some kappa sufficiently large. Okay? So these are kind of standard conditions that we've seen in other works, or similar to conditions in other works for considering sampling and other computational problems on random graphs. Okay? Okay, so this is the random graph model that we consider throughout this work. These are some examples that are included here. Of course, the delta regular random graph, these are a special case of this model where all the degrees are the same. We also have this case that I mentioned earlier, where if we plant, we get a random regular graph, and then we plant a vertex of degrees n to the, and say n to the epsilon, it satisfies the conditions also that in the previous slide. We have power law degree distributions, and also fit in this framework, and the Eddos-Rengi random graph, we provided with the probability of every edge is lambda over n, where lambda is a constant, also fits in this way. Okay. So some earlier work, as I mentioned, together with Risa, we did some earlier work that apply exclusively to random regular graph. And this work applies to every Q and all beta in the uniqueness regime. But there is also the work of Mosa's slide where they show that if you consider the global dynamics for the easy mode, the special case of Q equals 2, on the edges in the graph, they can prove this n to the 1 plus of 1 bound on the speed of convergence through the uniqueness regime too. And notice that this is actually matches the lower bound that we mentioned earlier. This is actually, there is an exponential on the maximum degree of the heterogeneity graph, which is log n over log n with high probability. Okay, so this is our main result. Essentially, for all Q greater than 2 and all beta in the uniqueness threshold, that corresponds to this to the average degree of the graph. Then we provide an approximate sampling algorithm that it's essentially has linear running times, and log n cube running time is the precise running time. So as a reminder here, we're working on random graphs, so our results will hold with probability 1 minus 0 of 1 over the choice of the random graph. So that means if we put a random graph with high probability, our bound applies to the running time of the algorithm. And notice, for example, that this improve what was known for the Edos-Renyi GMP model, right? Because it improved the running time for the Q equals 2 case from n to the 1 plus of 1 to n log n cube. But for Q greater than 3, there was no polynomial running time algorithm known, and we proved a near linear running time algorithm here. Okay, so now let's describe our algorithm. The algorithm is based on the global dynamics for the random cluster mode, which is a closely related mode to the ferromagnetic pods and easy mode. In this mode, configurations are the subset of the edges of the graph, and there are two parameters P and Q. And every subset of edge receives a weight, which is P to the number of edges in the subset, 1 minus P to the number of edges that are not in the subset, and then there is a Q factor for each connected component. And in this mode, we can of course define the corresponding global dynamics Markov chain, which for distinction we're going to call the FK dynamics. So this chain starts from a subset of the edges, picks an edge uniformly at random, and then it adds the edge with some probability. If the edge is a core edge, which is an edge that changes the number of connected components in the graph, then it adds with this probability, otherwise that with probability P. And if the edge is not added, then it is removed. Okay? So it's a fairly simple Markov chain for the random cluster mode. The reason that this is relevant, a relevant Markov chain for the pods mode, is that if we can draw a sample from the random cluster distribution using, say, the FK dynamics, then we can very easily transform it into a sample for the pods distribution. This is done by simply getting the edge set and then assigning a random spin independent to each connected component of the configuration, and for getting the edges, and that gives you a spin configuration. And it's not hard to show that this is a configuration from the pods distribution for a beta that it's related to be like it's shown here. Okay. Our main technical result actually is a tight bound for the mixing time of the FK dynamics on a random graph, right? And this tight bound is n log n. Remember that the mixing time is the number of steps the chain needs to converge. What that means is that we look from the worst possible starting point, the number of steps it takes for the top variation distance to get below 1/4. Okay, so the mixing time, and this threshold here, PU, is the threshold, the corresponding threshold to the uniqueness for the random cluster mode. In particular, we have the relationship between the uniqueness for pods and the uniqueness for random cluster. Yeah. So some notes on this result. Again, they hold with high probability of the choice of random graph. As I mentioned, the bound is tight. We actually prove in this result, we also prove a lower bound. The parameter regime is actually tight. It was recently shown that when P is above this uniqueness threshold, the mixing time of the FK dynamics becomes exponential. It requires exponentially many steps to converge. So we also prove the mixing time bound for an optimal range of parameters. And to transfer the results from the FK, from the random cluster to to the POTS mode, notice that there is this loss of a log square n factor, but this is because that's the steps of the FK dynamics are a little bit more complex, right? We need to check whether an edge is a core edge or not. But this can be done in log square n time, in log n square amortized time, using the dynamical connectivity, using result from the dynamical connectivity problem, like from 20 years ago. Okay, so now let's do a quick sketch of the proof. So the proof is a coupling proof. So we will design a coupling of the FK dynamics, and we will bound the coupling time. And this coupling will have two phases. The first phase is what is called a burning phase, which means that we'll run the chain, two copies of the chain independently, right? Until this chain achieves some nice property that then we can exploit to further analyze the coupling. And in this case, in this burn period, the goal is to wait until the configuration chatters. Suppose that you start from the configuration that has all the edges. We know that in the stationarity, there are no big components. Component has size order log n with high probability when p is less than pu. So we wait for some time until all the components are of size order log n. And we can actually show that this takes order n time. This is an improvement over previous work on regular graph where we're able to show n log n time. And in the second part of the proof, or the second part of the analysis of this coupling, we'll take two shatter configuration and then exploit the monotonicity of the chain to localize it to a ball around a vertex, and to use the analysis to understand what is happening, how mixing is happening in a ball around the vertex. And for this, the key observation here is that in the random graph, a ball is a tree or nearly a tree. So the mixing time is quite easy. A mixing time bound for dynamics is fairly easy to obtain. But we also need what is called a spatial mixing bound, which means that we need to show that the boundary at the boundary of the tree, at the configuration of the leaves of the tree, don't really influence what is happening at the root of the tree. Yeah. So with these two ingredients, especially with the second one, it's fairly standard to get a bound on the coupling. Okay. So the main contribution and the main ideas here are really about this shattering phase, which we analyzed earlier in the earlier work for the random regular graph, but there were some intricate difficulties to analyze, to extend it to more general graphs because the growth is not uniform. Okay, but the idea is to combine two different types of branching processes. This is a high-level idea. So we have branching processes that allows us to generate a random graph. We also have branching process that allows us to generate a random closed configuration on a graph. And the idea here is to combine the two branching processes, and as we generate the random graph, we try to also generate a random closed configuration on something that at least bounds the random closed configuration from above. And using this, you can show, for example, that using this idea, we can show, for example, that proof like static properties of the random closed distribution. But to actually prove something about the Markov chain, we need to extend this idea of revealing the random graph, but instead of revealing the random closed configuration, we need to reveal the configuration of the Markov chain at time t as we reveal the random graph. And the reason this is possible is because we can generate all the randomness that the Markov chain is going to use right at the beginning. Right? Let's say that we're going to look at time t. We can generate the t random edges that the chain is going to use, and the t random numbers between 0 and 1 that is going to use to decide whether to add or remove the edge. Okay, so here is the high level idea of the branching process. Suppose that we want to generate the component of a vertex p. So what we do is that we first generate a ball of constant size around this vertex, and we reveal the random graph configuration there, right? Then we assume that everything outside in the random closed is wired together, right? All the edges are there, so all the edges and all the vertices in the boundary are in the same connected component, which is kind of the worst case because of monotonicity. This is the worst case. It gives you the most connectivity inside, and then we'll run the FK dynamics just inside this ball up to 90 using the randomness up to 90 that affects this ball. Like, I mean, you want to look at the edges that are inside this ball, and we look at the random numbers corresponding to those times, right? And with these, we can generate a configuration inside this ball that by monotonicity we know that sits above the configuration of the chain, right? Okay, this is the first step of the revealing process. Then we're going to look in this random cluster configuration that we reveal, we're going to look which vertices in the boundary are connected to the center of the ball. And from those vertices, we're going to explore again. We're going to repeat, we're going to reveal the random graph, a ball around those vertices, and then we're going to simulate the chain in those balls, and so on, okay? So there are two key observations for understanding why this joint revealing procedure is useful. The first one is that if we do this in a coupled manner for all the vertices, like we do the revealing for all the vertices at the same time and coupled together, we can show that the intersection of the configuration of all these balls dominates the actual configuration of the chain. So whatever component structure we get from the intersection of all these balls dominates the true configuration, right? So in particular, if we show that all the components are small in this configuration, in the simulated chains that we run, then that would apply to the true distribution of the chain. And to obtain that the configurations are all, that the components are all small, what we do is we show that if we consider the branching process that corresponds to the vertices that we need to explore, right? In these slides here, we start from this purple vertex, and then we see how many blue vertex we have. And then we see in the next generation how many blue vertex we have. We can understand this as a branching process, and when we prove that this branching process is subcritical, which means that it dies out quite quickly and it has exponential tails. Okay, so and just a quick comment on the other ingredient here, which is also novel to this work, is that we needed this exponential decay, this spatial mixing property for tree or tree-like graphs. But the caveat here is that our trees are irregular, right? The trees have different degrees, so we actually had to show that there is this very strong decay on the probability of having a connection from the leaves to the root of a tree, of an irregular tree, whenever P is in the right range. So we get the right exponential decay, and it is important that we actually get the right rate of decay. Otherwise, the proof won't go through. And as a byproduct of this strong decay, not only will we get the mixing time result that we require, we also show that the uniqueness of the Gibbs distribution in this set of for this class of irregular trees. Okay. Thank you.